Hi to everyone, I'm Sergey Legtchenko. I will be presenting our work called Towards Paravirtualized Network File Systems. This is a work done at Microsoft Research Cambridge with Antony Rowstron and Raja Appuswamy. Raja is the main contributor of the work, but unfortunately he couldn't make it today to the conference. The context of our work is virtualized enterprise data centers. These infrastructures are typically composed of a set of compute nodes that are running a hypervisor layer, on top of which run a set of VMs. Within each VM, we have a guest OS that supports a set of applications. Often, storage resources within these infrastructures are disaggregated on a set of storage servers. And applications within the VM accesses the storage server remotely through the network, with typically 1 or 10 gigabit Ethernet networks. The mechanisms that are used to access remote data are mainly two. First of them is virtual hard disk, or VHD. This mechanism is transparent to the guest OS, and essentially for every hard disk within the guest OS, there is a VHD file, a unique file stored within the storage server. On the contrary, for the network file system, applications are explicitly aware of the fact that storage resources are remote and accesses them through a network file system client within the guest OS. And typically files are stored not within a single file within the storage server, but as a set of files. Typical representations of these protocols are NFS or SMB. These mechanisms are here for a long time, and basic properties and features are well understood. However, they are both heavily impacted by two main hardware trends that are currently emerging in data centers. First of them is persistent memory, enabled by technologies such as NVDIMMs, PCM, or Memristor. Not all of these technologies are currently available, but essentially some of them are. For example, NVDIMMs already exist. And the promise that is made by these technologies is that they will provide very low latency storage. So they advocate latencies in the order of magnitude of what DRAM proposes. They promise to be cheap with a cost comparable to what flash costs today, but with a greater reliability than flash. The second trend is the increase of performance of the networks in the data center. So in some data centers, we currently already have 40 gigabit Ethernet with technologies such as remote direct memory access, or RDMA, over Ethernet. And we expect this technology to scale to 100 gigabit per second in the near future. And thanks to RDMA, the latency is also very low, so typically in the order of 1 or 2 microseconds. And these protocols start to be well adopted by the industry with, for example, SMBD that supports SMB over RDMA or DAFS. So in that context, this work explores how VHD and NFS mechanisms work. Namely, what are the trade-offs in choosing one versus the other with these new emerging trends? And are these mechanisms at all sufficient with this very performant hardware? So for that, let's have a look in more detail on what happens when files are accessed with these mechanisms. So for more practical reasons, we give an example with a Windows stack, so running a Hyper-V and SMB client and server. So for a VHD, the application, the mechanism is totally transparent to the application. So when the application performs an access to a file, the request goes through the file system within the guest OS. which transform the access to the file into a set of accesses at the block level, then performs I/O scheduling and transmit these requests to the virtual block device driver. These requests are then transmitted to the hypervisor, which maps this request to the VHD file on a remote location through SMB and transmit the request through the network. Then on the SMB server, the request is mapped to request on the VHD file on the local storage and goes through the file system of the server. And then again is transformed to a set of block requests and executed. Now with these mechanisms, it's clearly shown that there is a nested file to block and then again to file translation. First time it happens within the guest OS, and then again it happens within the storage server. So we have an overhead of doing that on the data path. On the contrary, for the network file system, the application explicitly knows that files are remote and uses an SMB client within the guest OS. And the SMB client directly maps the access to the file to a remote location address and transmits the request through the virtual NIC, bypassing the hypervisor to the storage server. And then the storage server performs the usual mapping to a local file, which goes through the disk, for the file system and the disk driver on the block device. So with this mechanism, we avoid nested file to block translations. However, the hypervisor is no longer on the data path because it has no visibility on what happens between the SMB client and the SMB server. For the hypervisor, it's just network traffic. So to summarize, for the VHD, we have overhead due to this file-block file translation. And what perhaps even worse, is that recent work has shown that actually the performance becomes less predictable. Whereas for the NFS, we don't have these problems. However, this access mechanism is not compatible with interception-based features because the hypervisor is no longer on the data path. So we cannot have any second-level SSD caching, no dedupe. Snapshotting becomes complicated. So essentially, that's the main drawback of network file systems. Currently, VHD is the preferred mechanism in data centers because it provides full system virtualization and has all without any compatibility issues. However, there is an overhead that needs to be quantified. So in the next few slides, I will describe how we quantify the overhead on an architecture that mimics what happens in data centers today, and then in a second time on another configuration that mimics what happens with the new emerging hardware. So first, in the data centers today, we have an architecture with a simple configuration with one compute server and one storage server. The compute server runs Hyper-V, on top of which we run Windows Server 2012. On the storage server, we have an SMB server that sits on top of a RAID 0 array of 8 SSDs. And the two servers are interconnected through a 1 gigabit Ethernet switch. As a benchmark, we run I/O meter with a database-style workload, namely 100% random access with 67% reads and a queue depth of 8. For the VHD configuration, the I/O meter file is stored within the VHD. The VHD is stored on the SMB share. For the NFS, the I/O meter file is stored directly on the SMB share. So this is the performance. On the y-axis, we have the performance of the VHD normalized by the NFS performance, such that numbers below 1 shows that the NFS is more efficient, whereas numbers above 1 shows that the VHD is more efficient. And what we can see is that after 2 workers, we vary the number of workers that are running IO meter. What we can see is that for a number of workers that exceeds 2, we see the overhead of these nested file to block translations. However, very quickly, the network becomes the bottleneck. And the 1 gigabit NIC is saturated beyond 3 workers. And therefore, since the overhead of the VHD is no longer the bottleneck, the overhead remains very reasonable, so within 2% of the NFS. So certainly, in data centers today, VHD is a good solution because it is still not the bottleneck, but yet it is compatible with a lot of hypervisor seating features. Now, let's have a look at what happens with emerging data centers. We have a configuration as previously with a compute server and 1 storage server. The compute server, as previously, runs Hyper-V with Windows Server 2012. However, on the storage server, the SMB server now sits on top of a 20 gigabyte RAM disk to emulate what would happen with persistent memory. And the 2 servers are interconnected through 40 gig Ethernet with a Mellanox switch and 2 Mellanox NICs that enable remote access over RDMA. The config for the VHD is the same as previously. The IO meter file is stored in the VHD, and the VHD is stored on the SMB share. For the NFS, unfortunately, SMBD cannot do RDMA directly from a VM because SR-IOV support is not yet available. So we run IO meter directly on the host. However, we believe this is acceptable because recent work has shown that for ES6 server from VMware with direct path IO support, the virtualized perf has negligible overhead. So we believe it's still fair. Here is the performance. So as previously on the y-axis, we have the performance of the VHD normalized by the performance of the NFS. And we vary the number of workers. And what we can see is that in all the cases, the NFS protocol wins. And in the worst case, there is a 3x overhead in using a VHD in that configuration. And even as we increase the number of workers and the parallelism of I/O, still the VHD is not able to fully saturate the 40 gig Ethernet. So to summarize, there is a performance versus flexibility trade-off between these 2 mechanisms. VHD is compatible with most of the features, but however, with the new emergent hardware, it has a high overhead. On the other hand, with the NFS, we don't have this overhead, but it isn't compatible with features that sits in a hypervisor because the hypervisor is no longer on the I/O path. And so we asked the question: maybe we need another data mechanism that would have that would enable hypervisor interception like VHDs, but would avoid nesting of block to file to block translations. So in other words, why not para-virtualize the guest NFS client? So essentially, with the para-virtualized NFS client, the main NFS client runs within the hypervisor, and there is a lightweight guest NFS client that acts as a proxy and forwards requests to the hypervisor. It would perform a first-level DRAM caching, but cache misses would be propagated to the hypervisor NFS client. The hypervisor NFS client would perform the second-level caching with flash or persistent memory. And beyond that, on the data path, we would use existing protocols such as SMBD to forward requests to the NAS server. We believe this approach is non-invasive because the only thing that needs to be modified is the support for paravirtualization within the hypervisor and a lightweight proxy within the guest OS. And so all the other bits on the data path will remain pretty much as currently. So the advantage is clear. There is no longer trade-off, performance versus flexibility trade-off. We would ideally have the performance similar to NFS and enable feature compatibility similar to VHDs because the hypervisor is now on the data path. Now operations requests on files are propagated the whole way through the guest OS to the storage server. So we have end-to-end semantic awareness. All the parties know what operate on files, basically. This has several advantages. For example, we could imagine improving of caching within the hypervisor with semantic awareness of file instead of just random blocks. File servers would not need VHD introspection because files are already visible. And also, client could use these NFS protocol to share files between each other, things which is not possible with current VHDs because VHDs are opaque files and only meaningful to the VM that uses them. However, there are many challenges associated with the approach. The first obvious one is that we would need a low overhead guest to host I/O propagation. And we did an experiment when we run simply a guest SMB client sending to a hypervisor SMB server. And this approach is clearly not practical because it's 4 times slower than VHD. So we need specific mechanisms to do it efficiently. And then on file level protocols, if the hypervisor has persistent memory caching, how would we integrate the file level protocols with where leveling? In terms of snapshotting, should the hypervisor do this, or can the storage server do it? Because several NAS servers are actually proposing snapshotting today. And finally, how should we use the persistent memory cache? Should we address it at the byte granularity like DRAM, or more at the block level like SSDs today? And the final challenge is that we still don't have full system virtualization because the VM needs to boot from a VHD. So we don't think this is an issue for server VMs because they don't boot very often and mainly boot from a remote image that is not often modified. But it could be an issue for virtual desktop applications that are often rebooted. So to conclude, the new hardware trends change the landscape of data centers. We have low latency RDMA access and persistent memory emerging in the next few years. So we need flexible and overhead-free data access mechanisms. And we show that none of the current mechanisms is proposing this because NFS is overhead-free but puts the hypervisor out of the I/O path, whereas VHD has unacceptable overhead with new technology. And that's why we believe we need to propose something else that would address these issues. So we propose to paravirtualize the NFS client. It would provide both benefits of the both worlds. However, there's still a long way to go. Thank you.
Oh, I had a question. Can you clarify for me what is the protocol on the wire? Is it NFS V2, V3, or SMB2 or SMB3? Because I got confused somewhere along.
So I think it's the latest SMB that supports RDMA. SMB3, I believe.
Why is it called NFS then?
Sorry?
Why do you call SMB NFS? Is there a reason for?
Like a network file system. It's
okay.
not NFS. It's
okay. It's just a generic NFS term, not the NFS protocol itself, right?
Yeah.
Okay.
Exactly.
So this work was all done with Microsoft Windows, SMP?
Yeah, the whole infrastructure is Microsoft stack, so